I need to put reinforcement. So I need to bring innovation in terms of my machine also.
Which one is cost efficient? The traditional method of making a printing or the one you made here?
There is a need to big discussion here because here we did with almost 80,000 rupees. It's very cheaper one. Okay. Normally, if you make by brick and mortar, it comes to 2.5 lakhs costing by IPM. So it's cheaper. But again, if you go in the mass production, it becomes much more cheaper.
But then cost of machine is also there. That is a separate
Yeah,
thing.
so if you go for mass production, it can go even further down. But this machine is not complicated like metal 3D printing. It's a very simple machine. So if you have a chance, sometimes you can visit to my lab. It's a very simple machine. Okay, only you can travel in XYZ platform. The innovation that we are bringing in terms of extruder only. That extrudes concrete, reinforcement, we have some sensors that are collecting data, and then we are making digital twin out of that. The machine is very simple. It's just a gantry frame having one extruder in the middle. You can left, right, आगे पीछे, up down. That's simple.
So one centrifuge costed you around 80,000 rupees.
The one we made.
At IIT Guwahati.
And then again it's we can deassemble it also, or like you mentioned that.
No, the security post was not made like that. Sentry post was done like that. Security post already we assembled it. It's been glued.
Sorry, security post and sentry post are two different
Projects.
Right.
Sentry was for Indian Army. Security post is here in the Cambridge.
Sentry post are already given to army.
Yeah.
Which place, sir?
Here in Narangi we have an army group.
Right.
So they have taken it to high altitude area. So it's in Tawang now.
And how much is costed that sentry post, sir?
50,000.
50,000.
Because you see, I don't have to pay any. It's my material, almost best materials. We are getting fly ash from power plants. Fly ash best materials. So cement is hardly 10%. And the design, of course, we don't charge anything for the design. Once the machine keeps on printing, our job is done. And the design is the key. Okay, so it's an interlocking design. So designs are made in a way that you can even start. Someone can stand on it. Okay, maybe I will share some photographs with you.
Yes.
He will pass it to you. So you can see the designs. Even we tested with a case study that after we make the joint, 3 people were jumping on it. Because they were in the assumption that if someone simply hit the wall, it should not fall down. It should not disintegrate. Because it's simply interlocking. There is no bonding. So making the design and creating with that precision is also important. If you are creating with imprecise things, no, it won't fit together again. So as I said, for me, design is important as well as how I can make it more accurate. Because when you have a like male female joint, I mean you have to make it more precise. Otherwise, they won't fit together.
So for the printing of the security post, how much time?
Security post today.
Printing and assembling.
Only printing. Only printing today.
So you mentioned the use of coffee grounds in one of your projects. Could you expand on that?
So this project was given by him only, the student. He was doing a lot of tea and coffee. He was not working on the project. So I say, तुम तो कुछ काम नहीं करोगे. You do something on the tea and coffee. Tea coffee जिंदगी बिता दो. So then he said, sir, I will use this coffee ground to make my BTP project. I said, how? कैसे करोगे? नहीं sir, in the filament में मैं देखा हूँ. In the net, someone added this kind of coffee ground into the filament. So he started adding it. देखो उसमें क्या है ना कि of course his topic is good, but you can simply add into the filament. So there is a process need to be followed. उसको तुमको पहले ड्राई करना पड़ेगा. You need to remove all the moistures. You need to blend it properly. When two materials are blended, the blending accuracy is also important. So we have a blending machine here. Then I told you go use the blending machine. Then there are different stages to get a perfect filament diameter. So earlier he was making 3 mm diameter. Then he cannot use in the commercial 3D printer because we have to go with 1.75. Then we got a wire drawer. It's going to draw the filament when it's going to extrude from the molten chamber. So I can share his report. If you send me email, I'll share his report. So he made some cup using that coffee ground mixed filament. So he did last 6 months because although he didn't work. So when I say chai coffee mein zindagi bita doge, then he really did that.
So anybody has any doubts? Anything you ask? Anything? No one?
Sir,
हाँ
in the security course, it's a brick, right?
हाँ
Can't it be manufactured by extrusion?
extrude.
Like we can just extrude the brick from a machine.
That is what is being done, na?
But does it need a 3D printer?
No, 3D printing means like when you talk about shape, no?
Yes.
So, but you see, that particular shape, if you want to repeat, it's okay. But we do not want to repeat that shape. They need it, tomorrow you may need a different one. So, that is the advantage of machine, no? You can create more designs every time. If you're happy, you want 10 like that, go for molding. Good. So, you have to, I don't know, go for a wise decision. Actually, इसी को use करना है, बाकी उसको भी use करो क्या? Whenever you feel कि if I want to use 3D printing to make my life more simple, go for it. Because I am not selling 3D printing machine, na? So I can't ask you to use 3D printer all times. कुछ भी करो, जो कुछ नहीं करते कमाल करते हैं. चलो, thank you.
जो कुछ करते हैं वो कमाल करते हैं. I was going to ask how many cups of coffee and how many cups of tea per day did that student drink? इतना कितना पीता है? Are all the professors and the students in BTS, they seem to have a very the temperament seems to be the same, no? What temperaments? A kind of a more open and less structured kind of thinking style.
Means they are teaching in without any structure.
There is structure, but there's less rigidity in that structure. It's more fluid. Usually,
So how was the talk? You learned something?
Yes.
Right? So you might not believe my words, but then there are lots of experts, so you should understand their view what they are talking about. So the other thing, very important thing you were talking about, you talked about, of course you talked about this point. DDM, we'll talk about it, okay? We have been talking about this. We'll talk what he was trying to say. I'll talk. Direct digital manufacturing. Now, other speaker because Professor Ravi, he works on the electronics silicon, electronics hardware because you just see, I told you a very important concept of Industry 4.0. One of the key concepts is IoT. IoT is nothing but Internet of Things. Now slowly we are going to move. Now we are talking about IoT, but certainly we are going to move from IoT to IoT, which is Internet of all things. Which means that each and every product you see around you has to be connected. Right? So Industry 3.0 was owned by, material always drive a society, a civilization. The Bronze Age, Iron Age, right? I also talked about last, we were living in which age earlier? Steel Age. We see everything still, right? Steel Age. Now Industry 4.0 is about the silicon age of silicons. Who understand this technology, silicons, who wants it, they are going to not survive next 100 years. So he works in very similar area of IoT. How do we print, how do we start all those electronics components. So now I will invite our chairman to talk about this technology. Okay? Yeah. Thank you.
So, hi everyone, I am Ravindra, as your professor has mentioned. I am from nearby department, Triple E, Electronics and Electronics. I teach basically fabrication technologies there, and also teach undergrad on instrumentation and measurement, those kind of things. Okay.
He also teaches design, he comes to the design.
Yeah, I was teaching in your department in this for the masters in electronic product design. Students are there. I was teaching them design of sensors. And all. Okay. So basically, my area, as I just mentioned, is fabrication and mostly on sensors. Okay. So I use sensors, but I fabricate them mostly in our own lab. Okay. Less on buying and mostly on we make it. Okay. Starting from scratch, like as your professor told that you have a silicon wafer on which we fabricate something. Okay. So earlier most of this fabrication technology was based on lithography. Have you heard this word, lithography?
So it's very important technology. You know that lithography, what is lithography?
What it is? What it is?
Can anybody explain what is lithography?
You project something on some surface and you can remove some the surface which is not been exposed to them.
Perfect. So a similar thing we have used in electronics, where you have this lithography technique was very old, where people used to print something on stones. Okay. Same technique we have been using in electronics to fabricate small chips. Particularly, all the chips till now are mostly fabricated by lithography. Lithography is of different type. I will come on when I am in additive manufacturing later on. Just I am bringing you in the context. Okay. So lithography, as he mentioned, that you have some projection of light, you have say some stencil or mask, okay, and that the mask is projected on some silicon wafer, and it is something is printed on that. Okay, right? Same concept has been brought in electronics, where say for example you want say 2 FET, field effect transistors. Have you heard this word? Field effect transistors. This is one kind of transistor, forget about it. So you want to print a transistor A, transistor B and transistor C on a particular chip. Okay. This transistor has various components. Okay. What I can do is I can simply make a mask, and also to remind you that electronics is the area where we use every kind of material, starting from insulator, okay, insulator, semiconductors and metals. Okay, it's not that when I talk about electronics, I only use a semiconductor. I also heavily use insulators, okay, as well as I heavily use metals. Say for example, consider a small device, say diode. Okay, diode is a 2-terminal electronic device, right? Do you know what is a diode? You have a one junction. One is P-type semiconductor, another is N-type semiconductor. So you have 2 semiconductors. Okay, there is a junction that is a rectifying junction, and I am having 2 electrodes. The electrodes are metal. This PN junction is of semiconductor. Okay, and say for example I have 2 diodes, diode 1 and diode 2, and I want to fabricate that on the same chip. I have to give some insulation between them. Okay, so there this insulator comes into picture. Okay, right? Similarly, when I say MOSFET, have you heard? Metal oxide semiconductor field effect transistors. Okay, metal oxide and semiconductor. Metal oxide is insulator, SS is semiconductor. So in the same MOSFET is all all your mobile chips and your laptop chips are mostly made up of these MOSFETs. There have been various kind of FETs playing in the market, but mostly our devices are based on MOSFETs. Okay, so the same MOSFET chip will require all these things. Forget about this diode example. You have metal, semiconductor, or say insulator and your semiconductor. Everything is there in a same. So we deal with various kind of materials. Again, coming back to lithography, say I have a particular mask, okay, I have to deposit these materials, okay, at different time. Say at t equal to 0, I want to deposit metal. At t equal to 1, I may need some insulating material, okay, or say oxide, okay, and at t equal to 2, I may need to bring semiconductor into picture, okay. So that is why this lithography contains various things, and this exposure thing that your friend was mentioning doesn't always work, okay. So you have various specialized, photolithography coming into the picture. Okay, when I say photo, means it has something to do with light. Okay, so what we do is we use, UV light mostly to cure. Okay, I will not go into detail of lithography. Okay, because that is a semester course that I teach in an 8th grade course to remind you. Okay, I will just give you an overview. Okay, so now you have a UV light. Okay, you have some photoresists. Okay, photoresists are nothing but some polymers which can change its properties when it is exposed to light. It can be a positive resist or it can be negative, depending on if it hardens when it comes into contact of light, or it softens. Okay, when it softens, I can dissolve it in something. Okay, so this lithography has to be done inside a clean room. Okay, and when I say clean room, I mean that clean room of electronic grade. Okay, this room is very clean, right? This room is very clean, but I cannot call this a clean room. Okay, there are certain definitions for a clean room. Okay, so this clean room in a fabrication person's eye is a class, say 10 million clean room. When I say class of X, okay, class of 1000 or class of 1000 or 10,000, I mean that in a 1 cubic feet area, a particle of 0.5 micron or less is not more than that. Okay, try to understand, or sorry, 0.5 or more is not more than 1000. Consider this room. Okay, I am taking a space of 1 cubic feet. Okay, a volume. Okay, if there are more than 1000 particles of 0.5 micron or more size, okay, I cannot say that this is a class 1000 clean. Okay, so that is why I told that this can be a 10 million, because there are so many dust particles and all these things in the classroom that are not visible to us, and we are also wearing a simple jacket and pant without any shoes. So we are the biggest source of contamination in this class. Okay, we are actually contaminated. In an electronic fabrication area, you cannot you will not be able to manage these things. Okay, why I am telling you, say for example you have a chip. Okay, your device is say 500 nanometer. Okay, your hair itself is much bigger than your device. Okay, even a hair falls on your wafer. Okay, you are about to damage 1 lakh transistor. Okay, your transistor itself is just say 500 nanometer. I am telling you that is very big size. 500 nanometer is too big. Okay, usually nowadays technology has moved to 7 nanometer or even below. Okay, say if your hair falls, hair has a say size of say usually say some millimeter, say 10 millimeter or so, and then diameter is also something in micron. Okay, but that is visible. We can say that, see that. But the transistor sizes you cannot even see. Okay, so even one hair falls on your on the wafer. Okay, you have to start fabrication of about say 1 lakh transistor on that particular area. Okay, and that will disturb the complete wafer on which you are going to process. Okay, right? So that is why there are some gowning procedure while going inside a clean room. Okay, and this lithography was the oldest technique on which people have been fabricating. Okay, depending on need of resolution. Okay, I mean say what kind of resolution I need in the fabrication, different technologies has emerged. Okay, one I was telling a photolithography. Okay, now we are in the deep UV photolithography, deep UV lithography. Okay, when I say deep UV lithography, I will be using even UV light in the deep region. Okay, UV light is usually what is the wavelength of UV light in general? Right, some no even below like yeah 200 to 300, 400 something like that. Okay, I mean 400 to 700 is visible, right? So 200 to something 300 or 400. If I go below also, I will be going to deep UV, and depending on this wavelength that I am using, okay, I may go to deep UV X-ray also. X-ray lithography is also being used. Okay, so there are different kind of lithography being used. Okay, so this is in general how a IC is getting fabricated in the industry. Okay, now coming to the additive manufacturing. Okay, or we call it maskless lithography. Okay, where you don't need actually any mask and you fabricate something. Okay, I am giving some example. Okay, say I have a printer. Okay, now you know lithography, right? Basic lithography you know now. Okay, now so in the basic lithography you now know that you need a mask to fabricate something. Okay, right? The concept of maskless lithography emerged when electron beam lithography came into picture. Okay, as I mentioned that there is a photolithography, you have electron beam lithography. Okay, where you use in place of light or UV light, you are using electron beam. Okay, so there a hard mask was not needed. Okay, what people did is they directly make some CAD design, okay, of whatever device you want to print, okay, and then directly fed to the computer. That computer is connected to a scanning electron microscope as well as a electron beam lithography. Okay, the same system can be used for these two purposes. Okay, now at the same time I can see that what is being fabricated, okay, by using this electron microscope. Okay, at the same time I can also fabricate using this electron beam. Okay, from there this maskless lithography concept came, and now we are in the era of, as Professor Ajit has mentioned, that we are doing maskless printing of some electronic component. Okay, like I cannot say that I can print of this order like 7 nanometer or so, but say some devices like sensors that will not need that is not needed to be at 7 nanometer. You can have a very good sensors which is having dimensions in micron. Okay, like 250 micron. Okay, say for example I am giving you one example. I think that will be वो है क्या हाँ consider this kind of design. This is an electrode. Okay, people in working in the area of sensors as well as in very specific area of biosensors, they regularly use this kind of electrodes. Okay, here if you see, you don't need to actually go to nanometer level. Okay, these are two pads where you need to probe something. Even you might be knowing for a two probe measurement also. Okay, if you want to have 4 probe measurement, you can have 2 more electrodes over here. Okay, and these pad dimensions are in say 500 micron by 500 micron. Okay, this is pretty big. Okay, now if I want to print this, okay, one way is I will go to photolithography, and of course this below this you have insulator, you have a silicon wafer or say something a wafer of say material X, and on top you have this metal electrode, and on top you have some sensing material which is semiconductor. So you have all these things. Okay. Now say you want to make this. One way is to use photolithography. Okay, but you know, people have realized that to make this type of devices inside a clean room, okay, is not work. When you have to deal with nano devices, then only you should use this lithography facilities. Otherwise, this kind of thing can be printed by, you know, various printers that are available in the market. Electronic, and to print electronic grade materials. Okay, you have inkjet printer. Okay, so these printers fall in what category? I mean, your professor will teach, but I am just telling you randomly what printers generally we use. Okay, you have inkjet printers where the printing depends on, you know, what kind of substrate you are using, what is the temperature of your substrate, what is the viscosity of the ink that you are using, okay, what is the nozzle through which this ink is coming, okay, and what is the minimum feature size that you require. Okay, so your printer will depend on your substrate temperature, what kind of your substrate is, okay, and I mean I'm telling you in general, but it can depend on other parameters also, and what is the maximum size of nanomaterial that is present in the ink, the electronic ink. Because I told you that this has to be some metallic ink, for example. Okay, metallic ink, I mean, when you expect some metal in liquid form, okay, it is usually existing in term of, you know, either it is molten or it is in the form of some nanoparticle. Okay, like silver nanoparticle we usually use. Okay, okay, is it clear? I mean, I will not go in more technical, but I'm trying to keep it more general. Okay. Now, say for example, your the silver nanoparticle inside your functional ink that you are using is of maximum size is about 200 nanometers. Okay. Depending on what company's printer you are using, okay, they put it in the specification sheet that size, say the nozzle dimension is say nozzle through which it is coming is say of diameter X. Okay, the maximum size of the nanoparticle that it can eject is of size X by 100. Okay, so if the nozzle is of say 2 mm, it can eject say 2 mm by 100 size of nanoparticle. It cannot, otherwise it will choke your cartridge. Okay, so usually these inkjet printers are cartridge based. You have 20, you know, nozzles in that, and that the ink come out of that. Okay, and it can, we have printed in our lab, we can have very nice IDE structures, as well as we can print, you know, complete films on top of this insulator. Okay. Then there are, as I mentioned, that there are some constants in that. Okay, like there is a very harsh kind of constant on the viscosity of the ink that you need. Okay, like for example, if you have some silver nanoparticle, suspended in some liquid and which is giving you, viscosity in the range of say 2 cp or 4 cp. Okay, cp is nothing but centipoise. Okay, you cannot print that. Okay, there are some constant on that. Say for example, Dematic's 283 from Fujifilm, they will allow you to print only inks with viscosity say 20 cp or even more. Okay, so what people do to print this kind of inks is to use to mix some other chemicals which can make it more viscous, like ethyl cellulose, EC. Usually they mix. So what I wanted to tell you is, making electronic inks itself is a art. Okay, and then printing is, of course, you need design and all those things. Okay, yeah. So this is one kind of printer. Another kind of printer which is very popular in printing this electronic inks are aerosol jet printers. Okay. So aerosol jet printers are something which has very less constant put on its ink viscosity. Okay. So you can print nearly anything from 0.1 cp to 1000 cp. Okay. It has very less constant placed on the viscosity of that. Okay. So yeah, so then there are plasma jet printers and there are several other 3D printers also available. Some dragonfly is there from Nano Dimension. You can have a very good 3D print. Okay. So this is one aspect of electronic print. Okay, that I have discussed. But this is not the end. Okay. Nowadays, packaging is very important or very crucial in electronics. Okay, and when I say packaging, it doesn't mean that how these boxes are made and packaged. What I mean is, chip to chip bonding. Okay, say you have chip 1, chip 2, and there are 7 chips. Okay, how say transistors on chip 1 is communicating with chip 7. Okay, how this power is getting dissipated, how heat is managed over there. Is there any need to make heat sink and all? Okay, so packaging has become very important aspect in electronics. Okay, and recently we have launched a full-fledged course only on electronic packaging. Okay, so packaging is very important. In packaging also this 3D printing and all is being used. Okay, so I will not go in detail of that. I think we don't have that much time also. So I will end over here only. Okay. If you have any questions or something is in my discussion, if you find something interesting and you could not understand or you want me to elaborate, please ask me. Okay. Yes.
So you were mentioning about the silicon manufacturing processes.
Yes. Not silicon manufacturing. It's actually IC manufacturing. And in silicon, you are right. There is. I'm just giving you opportunity. Just give me 1 minute. Silicon wafer manufacturing is a separate line. Okay. Where you as you have heard that silicon is made from sand. Okay. So that is a separate process where you take sand and actually not sand, actually it's quartzite mineral, okay, and then quartzite is being turned into metallurgical grade silicon, and then this metallurgical grade silicon is turned to electronic grade silicon by a process which is very popular in industry. We call it Czochralski method. Okay, then there is one more method, we call it float zone method, where we fabricate, these wafers by molten silicon. Okay, and then we get single crystal silicon from quartzite.
So material process classes we discuss about single crystal material, how it is made. Remember, I showed you the video of how it is done. That is the way of making wafer. So they make sure that the purity level is around 99 point something.
and
Yeah.
then do the slicing of wafers.
We know that Taiwan is far ahead in these manufacturing of
Yes,
this,
yes.
and by a wide margin from Intel and even Samsung and all. So, what is that technology barrier, and why others are not able to meet that technology?
Yes, very good question, and we are having good collaborations with Taiwan, and I can easily, answer these questions at least from my point of view. Okay, but this is a very general question, and someone in the government should also ask from them that why this is happening. Okay, so but this is non-political. Please don't record. Okay. So yeah, so what I want to mention here that it is true that not only India but many countries have missed that semiconductor bus. Okay. See, this in the semiconductor fabrication line, if you see, there are various things. Okay. This fab that you are talking, that Taiwan is leading, is only one part. Okay. Then you have design. Before fab, design comes. Okay, design. Then you have fab. Then you have assembly lines. Then OSAT, ATMP. There are various there is a complete line. Okay, all these companies, Qualcomm, ST Microelectronics, all these giant in the area of IC fabrication, they all have offices over here, big offices. Okay. But what they do design. They don't fabricate. Because fabrication is something where lot of investment goes in. Okay. Say I am giving you one example that if at this moment if I want to establish a technology of say 45 nanometer node, which is much beyond than what is being used. Okay, I will at least need something like 10 lakh crore rupees. Okay, with all the, because I mentioned that most of the money goes into maintaining these clean rooms. Okay, a chip which is fabricated, say a chip of say 250 nanometer, which is getting fabricated at 250 nanometer. Say for example, for that I need a clean room of class 100. Okay, I need a clean room of class 100. If I go beyond 250 nanometer, say I come to 200 nanometer, I will need a clean room of class say 10. I cannot convert this clean room of class 1000 to clean room of class 10 because both will need different technologies and different kind of filters and all these things are required. Okay. Now, moving from class 1000 and making a class 10 clean room, okay, it takes say about say 1 lakh crore rupees. Just moving. And then, if say Intel in US is moving from say 10 nanometer node to 5 nanometer node, and then I have to move everything, my industry to 1 nanometer, okay, and for that I have to go from class 100 or so class 10 I was using to class 0.1, and then I will need more investment. Okay, so this industry is very, very dynamic. Okay, it's not that कि एक बार establish कर लिया and it's a milking cow. It's not like that. Okay, it's very dynamic. Okay, and the designers, they always come with something. Okay, see, as I mentioned that Qualcomm and all these companies are designing in India. Okay, but the design has to be feasible. It's not they are designing something weird. They are going and getting that approved from, as you mentioned, Taiwan has say TSMC, for example. Okay, they are going and validating that in TSMC that this line can be fabricated, and then TSMC becomes interested and they have another plant over there. So now they are, Taiwan. For the TSMC, Taiwan is becoming very small, so they are moving to Germany and other uh, 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 countries. And then coming back to US, in US this concept of Fab Lab was I have read this. There is a book on 75 years of transistor, and they have, I mean, everything from it. It is coming from IEEE, and they have mentioned these things there. Okay, so in US their plan was like you have 4-5 universities. Okay, say 100 kilometer apart. You make a Fab Lab in center. Okay, so these 100 universities, you are hiring people from this these 5-6 universities, which is say 100 kilometer apart from you. Okay, and then your work is going ahead. But now, when things are changing, people can move from here and there. Okay, this concept has vanished, and these companies are mostly say. I mean, Global Foundries is something which is giving a good fight to TSMC, but then also TSMC is far ahead. Okay, there are no more foundries, not much foundries where you actually fabricate. But yeah, so what India is trying right now is we have SCL in Chandigarh, semiconductor lab in Chandigarh. They are trying to revive that at very high node, like 500 or something. Okay, and then what we can do is at least we can have this OSAT where you do testing and packaging and all those things. Those things we can do, okay, with the help of government. But fab is something I think it will take time. Okay, we have a small fab. Yeah.
Start with packaging. India has to start with packaging. How to package? Fab lab maintaining is not so easy.
Yeah. So
India is more interested into establishing fab lab, which could be around 50 to 60, 70 nanometer for automotive sector, not for electronics, mobile. How much is the mobile nanometer? Do you know that? How much? 4 nanometers. No, iPhone 15 is a 4 nanometer chip. So it follows a Moore's law basically. That every 2 years your chip size will increase by half, right? By half.
Yeah.
So next 2 years it has to 2 nanometers. Such a dynamic industry. So for 2 nanometer, what is saying Clinton again changes. So we are talking about 4 nanometer, and what India is now looking for 60 something nanometer.
Yeah. So was I able to answer you? But this question is something which is haunting everyone who is working in this area. Okay, but that is not. Yeah. Yes, please.
So, if our country doesn't have the capability for these high-level chips manufacturing, if other countries stop supplying, then is there any kind of a backup plan?
So, thanks for asking this from Secretary of Ministry of Electronics, but unfortunately I have time for that. So, actually this is you have rightly asked this question, and say like 1 year back I was trying to book one car that was very popular that time, Scorpio M. It was not released, but it was about to come. And then I have heard that there is some delay in supply of some semiconductors, and that is why I moved to another vehicle. But now I'm happy that I did not choose that. But anyways, so semiconductor line disturbance is always something which India is considering with priority, and that is why you are hearing so many buzz of regarding this. Okay, lot of conferences, lot of gathering of ministers and people working in this domain are going on. Okay, I am also going in Fab in SCL Chandigarh. I told you there is a big gathering on packaging only, and these conferences are very selective. Like they are sending invite. It's not that the conference is free. I mean, just you have to gather, to improve this. So government is pushing it like anything. Okay. So I think soon we will catch something, and once we start, I think then things will be okay. It's not that Fab Lab is something we cannot have, but ultimately these companies has to establish. Government can't establish these things. Government has nothing to do with it. Okay, companies. So what government can give is they can try to bring these companies in India and give them some faith that okay, we will give you complete ecosystem. Okay, so Taiwan and all, they have started much early. So that is why because this, as I told you, say for example, as I mentioned this lithography and all, the cost in initial investment is too high, but then also mobile cost is very very less, because this is kind of milking cow. Once it is ready to give you say you started with 5 nanometer node, you have a design, you will have initially so many batches of wafers will go back, you will not be able to use that. Okay, but once you validate that and your process is optimized, okay, you can fabricate a number of chips in one go. Okay, so this lithography is a batch fabrication process. Similarly, this printing, I told you, particularly people in if you have seen this flexible LEDs or flexible or say bended kind of displays. Nowadays, these foldable phones are coming. Okay, there this kind of printers are playing very important role. So particularly for roll-to-roll fabrication of displays and foldable devices or wearable devices. Okay, so it's not that these things will not be able to come to India. It will come, but government is pushing it very hard. Ministers, they are attending all the conferences. Okay, so yeah, but then when you talk about complicated systems like microprocessors, microcontrollers, those things will take time. But anyways, we are not. We are late, but we are pushing very hard.
Right. There are 3 national policy which Indian government has. Three areas of national policy. Of course, one is the semiconductor. So 3 important technology for this century. Semiconductor has, and then other is of course additive manufacturing. Semiconductor additive manufacturing. What is third? So it's energy, hydrogen energy, green hydrogen energy. So there are 3 important national policies for Indian government. They are pushing everything on these 3 area technology. So these 3 areas are very, very important for the future. Any other doubt? Any other things? Anybody want to ask? No doubt? Okay then. Yeah. Thank you. I hope you got to know something. How the design was, how the design was. So we'll meet tomorrow is holiday, right? Yes. And please upload your assignment which I have given. It's already in Teams, and we'll meet next Sunday. Yeah, thank you. Bye-bye.